Welcome to the class where we will discuss the topic of the Laplace transformation. The Laplace transformation allows one to determine the value of a function in the domain of a complex variable. That is, we can pass from a function in the time domain to a function in the domain of a complex variable. By definition, this requires calculating an integral. However, we will only use the definition in the first two tasks, and in the subsequent ones we will use the properties of the Laplace transformation. The basic property is linearity, that is, the transform of a sum is equal to the sum of the transforms, and if the function is multiplied by a constant, then this constant can be pulled out before the transformation. And at this stage, I would like to draw your attention to the nomenclature. Transformation is an operation, and the transform is the result of that operation. This slide shows four more properties of the Laplace transformation: shift in the time domain, multiplication by time, change in the time scale, shift in the frequency domain. In each case, the function f of s is the transform of the pure function f of t. In the last two cases, wherever a complex variable s appears in the formula f of s, we must substitute the expression given in brackets. And why are there so many properties of the Laplace transformation? Well, precisely in order to don't have to calculate the integral. In the case where the function is periodic, one must first calculate the transform of the first period of the function, f1 of s, and only on this basis can one determine the transform of the entire periodic signal. The last two properties are calculating the initial value and the final value. For the initial value, one should simply use the formula. However, before we start calculating the final value, we should check whether all poles of the expression s times f of s are in the left half plane of the complex variable. If so, then one can proceed to the calculations, and if not, then the final value doesn't exist. And that is the end of the theory. In the dozen examples that I will show you in a moment, I will try to show you how to use this theory. Let's start with the following task. Calculate the Laplace transform of a unit step function. But before we start the calculations, we need to know what this unit step is. It is a function that has a value equal to 0 until time 0, and from time 0 it has a value equal to 1. In this task we will use the definition of the Laplace transformation. Our function is unit step. So what is next? Please note that the integral is on interval from 0 to infinity, and the unit step in this range has a constant value equal to 1. At this point, we need to use one of the integration methods, specifically integration by substitution. In this method, we substitute a variable for an expression. What variable should be used? Any variable. Let's use the variable flour. Let this expression be the entire exponent, since we should know the integral of e to the power of the variable. Below we calculate the derivative. d flour is equal to minus s dt. This equation is needed to have something to substitute for dt, so it needs to be transformed. These types of tasks can be solved in two ways. Either the integration interval must be recalculated for a new variable, or after calculating the integral, one must return to the previous notation. I will use the second approach. This minus s is a constant, so I pull it out before the integral. The integral of e to the power of flour is e to the power of flour. But we don't know within what limits. Let's go back to the previous symbols and the previous interval. Let me remind you that we need to subtract the lower limit from the upper limit by substituting these values into a variable, and the variable is t. E to the power of negative infinity is 1 divided by e to infinity, so 1 over infinity. And 1 over infinity is 0. E to the power of 0 is 1. And this is the formula for the unit step function in the complex variable domain. Originally, there was supposed to be a task here in which the transform of the linearly increasing function is calculated, but after recording, it turned out that it was impossible to show it in the time available. So, since the recording is already finished, I pasted it at the very end of the video, and here I will only show the result, which will be needed in subsequent tasks. If a linearly increasing function is given The formula of this function is the Laplace transform of such function is and please remember this because we will need it in subsequent tasks. I will write in a moment what the Laplace transform of the Dirac delta is, but first let's say what the Dirac delta function is. It is a function that has the value infinity at time 0 and the value 0 at all other times. To determine the Laplace transform, even longer calculations are needed than in the previous task, so I will not show them now. You can find the full solution in the script. However, please remember that the Laplace transform of a Dirac delta is equal to 1. In further calculations, it will be necessary to know all three transforms that we talked about today: Dirac delta, unit step, and linearly increasing signal. Please remember them and treat them as known values during calculations. No need to derive them. The next task is to calculate the Laplace transform of the function shown on the left. Generally, there are three different approaches to this type of task, but due to lack of time, I will only present the mixed method here. I have presented the analytical and graphical methods in other videos. First, we will try to split this function into arrays whose sum will give us exactly this function. We don't need to worry about the first part of the function, which is 0, because the Laplace transform of 0 is 0. So the first array will start after a time equal to 2b, where the letter b is just some constant. The first array always lines up perfectly with the graph. But the thing about array is that, once it starts, it doesn't end. Therefore, when drawing subsequent arrays, you must also take into account those that have already been drawn. Each subsequent array begins after a time at which there is a discontinuity or breakdown of the function. This means that the second array must start after time 3b. And at what value will this second array begin? It must be such a value that when summed with the first half-line, it gives the value of the function c of t at that time. This array will start at value 0. Because minus 2b plus 0 is minus 2b, and that is also the value of the function c of t after time 3b. Now we need to determine the slope of this array. For this, we need to consider the value of the function after time 4b or almost 5b. Let's consider the value of the function after time 4b. The function c of t has the value 0. Therefore, the sum of the first and the second arrays with respect to time 4b must be equal to 0. The first array after this time has a value of minus 3b. Therefore, the second array must have value plus 3b. And now we just need to draw an array that passes through this point. The third and last ray will start after time 5b, but to calculate the value at which it will start, one must first determine the values of the first two rays after time 5b. The second ray has value 6b, and the first ray has value minus 4b. So the last ray must start at minus 1b, because then the sum of all three will be 1b. Now we need the values of the previous rays after time 6b. The first has a value of minus 5b, and the second has a value of plus 9b. Hence, the third ray must have a value of minus 3b, so that the sum of all of them gives us a value of 1b. We did it. We have three rays whose sum gives the function c of t. Now we need to write the formulas of the individual lines on which these rays lie. Let me remind you that the formula for a line consists of a slope, a variable, and the intercept with the vertical axis. For the first line, the slope will be negative because the line is falling. Its value is the tangent of this angle, and the tangent of angle alpha is the value of b divided by the value of b, which is 1. I don't have to write it, but it will be more readable. The variable in this graph is time t. And where is the intersection of the line with the vertical axis? In the value of plus 1b. And we have the first formula. We proceed similarly for the second line. The slope is 3, the variable is t, and the vertical intercept is, it will be low, but it can be calculated that it will be in the value of minus 9b. And I do the same with the last line. The slope is minus 2, the variable is t, and the vertical intercept is plus 9b. Now we can move on to analytical calculations. First, let's write the function c of t. I will write the first component, and in a moment I will explain where it comes from. The first bracket is the line equation, but we don't want a line, only a ray, and that is what gives us the unit step. We all remember what a unit step function looks like. And in this problem, we use the part of the unit step that is for negative arguments. Therefore, if the unit step argument has a negative value, then this unit step will be 0. Please look at what I wrote. If time t is equal to, for example, 1b, then in the brackets there will be 1b minus 2b. that is, the value minus b. That is a negative value. So, for time 1b, this entire unit step will be 0. And that is very good, because on the graph we can see that for time 1b, this first ray doesn't exist yet. That is, it is equal to 0. And in exactly the same way, one should write the remaining parts. The second ray starts after time 3b, so I will put 3b here. At this point, I would like to draw your attention to the way of writing. If I write the number 1 and then open a bracket right after it, I assume that it is a unit step function. However, if I want to multiply 1 by a bracket, I have to put a dot there. Please be careful with this notation, as I often cut off points in the test for it. Let me remind you that the time shift property is so we see that in order to use this property, the unit step expression must be the same as everywhere else where time appears. And simplifying from the point of view of this task, both brackets must be identical. However, we can only transform the first bracket. This unit step function cannot be changed in any way. The unit step will be the same throughout the whole calculation phase. To make the calculations more readable, I will deal with each component separately. We start the transformation by extracting the coefficient of the variable t from the first bracket. In this case, it is the value minus 1. In the second step, enter in brackets what one would like to obtain. But we still need to add something here to make it mathematically correct. In the last step, one needs to break the first bracket into two parts. Firstly, the first part. And now the second part. I wrote the constant b in brackets to emphasize that it should be multiplied by what was before and after the brackets. And we can now apply the time shift property to these two components. In the first case, it is visible, but in the second case, it may not be so obvious, because there were supposed to be two identical brackets, and here it is no such situation. We only see the delay, but no function. I will try to explain it this way. Can I multiply the second component by 1? I can, because it won't change anything. can we multiply this by a unit step? This would mean that we would have multiplying two such functions. Whereas 0 times 0 remains 0, whereas 1 times 1 remains 1, and in the range where we multiply 0 times 1, the result is 0, so the result will not change. And can this be multiplied times a unit step, also delayed by 2b? Yes, because if we look at the graph, the product of two such unit steps will not change anything. And we have obtained a form that can obviously be used for time shift, where the function f in the formula is the unit step. There is no need to write it like that. It is important for you to know that you can use the time shift when you only have one unit step eventually multiplied by a constant. Now let's move on to the second ray. I put the constant next to the variable t outside the brackets. And we see that both brackets are the same, so nothing more needs to be done here. And the last component, we proceed in the same way as before. Now all we must do is write the result. Please always pay attention to the letter that the function is defined with and the letter case. Since the function in the time domain was c of t, then the function in the complex domain is c of s. All functions in the time domain are denoted by lowercase letters, and all functions in the domain of the complex variable s are denoted by uppercase letters. The transform of a sum is equal to the sum of the transforms, so we can deal with each component separately. The first component is here. First, we write a constant, in this case -1. Next, we need to write the delay according to the formula, which is e to the power of minus s times delay. In our case, this delay is 2b, so and finally, we need to write the function f of s, that is the Laplace transform of the non-delayed function. Our delayed function is t minus 2b, so the undelayed function will be t itself. And what is the Laplace transform of the function t? We calculated this earlier, and it is equal to 1 over s squared. We do exactly the same with this second component. First, the constant and the delay. In this case, the function is a unit step, shifted by 2b, so the undelayed function is a regular unit step, and its Laplace transform is equal to We do exactly the same with the remaining components. If the task content includes that the result should be on one fraction line, and it probably will be, then the result must be presented in that way. The common denominator is s to the second power. And this is the Laplace transform of the function represented by this graph. A task can also be represented using a brace. In such a case, to write the entire function as a single equation, one needs to add the individual functions with a delay when they are activated and subtract them with a delay when they are deactivated. The value 0 can be omitted, so we start from the second line. and similarly for the remaining conditions. Now, each of these components needs to be transformed into a form in which the timeshift property can be used. Now I will not calculate it any further, because it will take a lot of time, but I hope that based on the previous task, you can already know how to do it. However, if anyone would like to check the answer, please go back to the previous task, because it is exactly the same function. Here, however, I wanted to show you that the task can also be given in the form of such a bracket, but it could also be an already given equation of the type I wrote at the end. One more quick task related to reading functions from a graph. Please note that on the vertical axis there are no multiplies of the constant a, but there are regular values. This causes the slope to be not 1, but 1 over a. Whereas further actions are the same as before. Now we will move on to tasks in which the properties of the Laplace transform will be used. In the first task, one needs to calculate the function, that is the Laplace transform of the function r of t, where the Laplace transform of r1 of t is equal to Please note that the task content didn't contain command to calculate the Laplace transform, which could be written as but the function that is the Laplace transform must be calculated. That is, it must be denoted by Please pay attention to this so as not to lose points for the task unnecessarily. However, if the task content includes the command calculate the Laplace transform of the function, then both of these notations will be correct. So I personally recommend always using the latter. Let's get back to the task. Here we should use the property of multiplication by time. So for our case, I assume that the derivative of the quotient was already covered in class, but to remind you, it is derivative of top times bottom minus top times derivative of bottom over bottom squared. Typically, the task will state that the result should be on one fraction line and sorted by powers of s. I draw attention to this here because I mean something slightly different than it is commonly understood. What I mean is that both numerator and denominator should contain only one variable s to a given power. Therefore, in the numerator we must add them together. If for some reason it could not be added normally, the s to the given power should be extracted in front of the brackets. Furthermore, no multiplication of the variables s can be left, so denominator must be multiplied. This form of the result is already correct, because each power of the variable s appears only once, and there is no multiplication of the variables s. Please note that the order of the powers doesn't matter. This form of the result is also correct, because there is no multiplication of the variables s anywhere, and only the parameters of these variables are multiplied. However, this form will definitely make it take longer for me to check the work. The next task is to calculate the Laplace transform of the function The property we need to use here is shift in the frequency domain. This formula means that wherever there's an s, one should substitute the expression s minus a. In our case, a is equal to minus 1. Therefore, in the next task, we will use change in the timescale property. Let's calculate the transform of the function w from t. According to the formula, in each place where a complex variable s appears, we must write s divided by 2, as well as 1/2 in front of the whole expression. Now let's move on to a slightly more complicated example of a task using the properties of the Laplace transformation. It is necessary to calculate the Laplace transform of the function a of t. If tasks involving sine or cosine functions appear, you can assume that the Laplace transform of the required function will be given in the task content. How should one solve this type of task? Step by step, that is, we use subsequent properties of the Laplace transformation. At the beginning, a change in the time scale. So, now multiplication by time or shift in the frequency domain. It turns out that it doesn't matter. Each order will give us the same result, as I will show you in a moment. For the first time, I will start from multiplication by time. Please make no mistake, this cannot be shortened. It will hurt, but it is necessary. I will use Pascal's triangle. Now I will calculate the same thing, but in a different order. As you can see, we got exactly the same result. Now I would like to show you a slightly different approach to two short tasks. Suppose our task is to calculate the following Laplace transform. We would like to use a shift in the frequency domain, but the problem is that there is no function with respect to which we performed the calculations. But are you sure there is no such function? Can we multiply that by 1? Of course. And can we multiply this by a unit step? The answer is also affirmative. Although a unit jump will zero out everything that occurred before time 0, we will actually always assume that before time 0 there is one big nothing, that is 0. Therefore, multiplying this function by a unit step will not change any value. We know the unit step transform. And for each variable s, one have to substitute s plus 6. And that is the end of this task. The situation is very similar if we wanted to calculate the Laplace transform of time. We have already calculated this, but it was very time-consuming. And what if we used the multiplication by time property? Again, the second function is missing, but we already know what to do in such situation. We can therefore see that this very time-consuming task using definition can be calculated in a dozen or so seconds using the properties of the Laplace transformation. In the next task, we will calculate the Laplace transform of the periodic signal shown in the graph. We will use here the formula given earlier, where f1 of s is the Laplace transform of the function first period, and tau is the period length of the periodic signal. So I ask everyone to think about how long the period of this function is. That is 6x. And when does the first period of a function begin and end? It starts at time 0 and ends after time 6x. It was drawn in such a way that it may confuse some people, so I'm showing it here. So let's write the first period in time domain. And a very important thing in the case of periodic functions is that the first period must be zeroed. The function is very simple, so we can immediately calculate the Laplace transform of the first period. whereas the transform of the entire periodic signal is equal to Finally, we will address the issue of the initial value and final value of a function. When we talk about an initial or final value, we mean the value of a function in time domain, but we can calculate this using the function in complex variable domain. Suppose we are given a function p in the complex variable domain. And our task is to calculate the initial value and the final value. The initial value of this function in the time domain is equal to... Sorry, but this is what my little p looks like. There is no need to write this limit, I just wrote it to make it more readable. At this stage, one needs to pull out the highest powers of the variable s before the brackets in numerator and in denominator and shorten them. And this is our initial value. However, to calculate the final value, we first need to check whether all poles of the expression s times p of s are in the left half plane of the complex variable. But what are poles? The poles are such values of the variable s that cause denominator to be equal to 0. We don't need the exact values of the poles. it is important that both poles are in the left half plane of the complex variable, so the final value exists. If the task content states that the object is stable, or that all its poles are in the left half plane of the complex variable, then the stage of calculating the poles can be omitted. Just like before, this doesn't need to be written. At first glance, it may seem that the result will always be 0, but we only need to consider a slightly different example to see the difference. The poles are 0 and -5/7. All poles should be in the left half plane of the complex variable for the final value to exist, but all poles of the expression s times r of s. So we see that this condition is met. And that's all I wanted to show you during this class. Thank you very much for your attention and have a nice day. We will calculate one more task based on the definition. The task is to calculate the Laplace transform of a function f of t, and this function is given by the graph First, one needs to determine the formula of the function. This is a linear function, so the formula for a linear function fits here. Now we just need to plug the right things into this equation. On the vertical axis is the name of the function f of t, and on the horizontal axis is our variable time. The slope is the tangent of angle alpha, so it is the ratio of the side of length a to the side of length 1. the intersection of the function with the vertical axis is 0. Therefore, we have a function formula. The Laplace transform is by definition the letter a is a constant, so it can be pulled out before the integral. And now we are at the point where we need to use the second method of integration that you should know, integration by parts. Let me just remind you that integration by parts involves using a formula like this. At first glance, this formula seems useless, because from one integral we create another integral, and an additional expression appears. But the point is to divide the function under the integral into two parts, so that the derivative can be calculated from one part and the integral can be calculated from the other, and as a result, an integral that is easier to calculate than the original one. In our case, we have a variable t and e to the power of minus st. Which part's derivative will simplify the entire expression? Yes, from variable t. So let's mark these two parts as a triangle and a square. Or no, let's use some normal letters. S and closed U. From the first part, we need to calculate the derivative. And one must calculate the integral from the second part. The integral of d close to u is close to u, and the integral of e to the power of minus st dt? No, it won't be 1 over s, because in the previous problem we had a definite integral, and here we have to calculate an indefinite integral. At this point, of course, you can do the calculations for this integral on the side, but if the integral is relatively simple, you can calculate it by trial and error method, what is of course not recommended, but I want to show some possible approaches to the same thing. The integral of e to the power of something is usually e to the power of something. So let's assume that our result is e to the power of minus st. And since this is the result of the integral, the derivative of this should give us the initial expression. Times the inner derivative with respect to the variable t. We can see that the result is almost correct, only the minus s doesn't match. So let's try again, but first divide by minus s. This time we managed to obtain the correct function, that is, we found the result of integration. Therefore, closed U is equal to we use the formula given earlier. But we had a definite integral, so everything that goes outside the integral must be on certain interval. We subtract the lower limit from the upper limit. And what is the upper limit? We substitute infinity for t, so we have infinity times 0. So we have a problem. Let's rewrite this expression. Let's deal with the first limit. How to calculate it? One option is to use L'Hopital's rule, but for that we need numerator and denominator, so we calculate the derivative of numerator and the derivative of denominator. Of course, the variable is t. We have two expressions depending on t. So here we have the derivative of the product. The result is the derivative of the first times the second plus the first times the derivative of the second. S is a constant, so what happened? L'Hopital's rule was supposed to help, but we are in a worse situation than when we started. Furthermore, we still have multiplication of infinity times 0, and on top of that we divide it by 0. The reason is the incorrect use of L'Hopital's rule. To use it, one must have a quotient of 0 divided by 0, or infinity by infinity. So we have to go back. We must have division of infinity by infinity. And now we can use L'Hopital's rule. Denominator is infinity, so... Okay, we have the first limit, now quickly the second one. We got this result. But is it correct? It turns out that again it is not, because when we look at this limit, it takes a determinate form. We have 0 times e to the 0 power, so the correct result is 0. However, you could see that if we use L'Hopital's rule in a situation where it is not necessary, we can obtain a completely different result. Therefore, both limits were equal to 0. We already calculated this integral in the previous task. And then we got 1 over s. And we succeeded. We have the Laplace transform of a linearly increasing function with slope a. However, what if we wanted the first period to start at time 1x? This is also possible, but one have to remember this short function fragment at the beginning. I wrote b11 because it will be a different function than b1 written above. Let's reduce this to a common denominator. We got exactly the same result as before. And when talking about periodic functions, I would like to warn you that task can be given in the form of a graph, as an infinite sequence, or using braces. So the content of this task could be given as but it can also be written as